Hello everyone and welcome to this webinar on advanced seatbelt modelling in Oasys PRIMER. My name is Richard and I'll be your guide for the next 48 minutes. All our webinars are recorded and available to watch on our website or YouTube channel. For the lucky ones watching live today, you'll see you're muted. If you have any questions, please type them into the chat and I'll try to answer them at the end. If you're watching this on YouTube and you have any questions, please leave us a nice comment down below or reach out to our support teams using the contact details at the end of the presentation. Today's objective is to introduce the latest capabilities of Primer's seatbelt fitting tool. If you're just looking for a quick overview, there's already an 8-minute video covering one of today's examples on our YouTube channel. Today's talk is mainly directed towards existing Primer users. There are two other excellent webinars on our channel by my colleague Ben Crone that cover a wider description of the seatbelt tool and typical usage. We'll leave links to those in the video description below. Today I'll first cover the motivation for using fully fabric seatbelts, then some examples. In the first I'll fly through the fitting process to give you a quick overview of how things work. In the second child seat example, I'll talk you through the whole process with a bit more discussion about fitting options and material properties. Finally, we have two rear seat examples where I'll cover a few points that haven't been mentioned yet. The last slides show you how to find out more information and I'll cover any questions at the end. First, a little background into why fully fabric seatbelts are interesting right now. There's increasing demand to better simulate the kinematic behaviour and injury of dummies like Thor, shown on the left, and human body models, shown on the right. Thor has load cells to measure injury directly under the lap part of the seatbelt, right next to the slip ring. Human body models have very soft tissue in front of more realistic bone structure. Child seats have convoluted belt paths and rear occupants sit right next to the slip rings. Our customers have told us that they struggle to get the right results with traditional 1D and the more recent 2D seatbelts. They also want to further their research on realistic seatbelt systems. A common problem with 1D slip rings is belt runout, as shown on the left. This can occur when the buckle slip ring sits close against the pelvis. We need fabric shells to contact the dummy, but fabric doesn't pass through the 1D slip ring when the pretensioner pulls the belt in. The belt will jam when the fabric reaches the slot. You can work around this to some degree by overlapping the 1D belts and shells, but it can get messy pretty quickly. 2D belts, as shown on the right, can be used in some situations to get a better result, but one common issue is their instability during unloading, as we can see here. We all know how difficult it can be simulating the friction at the pelvis buckle using just one lumped parameter in a 1D or 2D slip ring. Recent versions of DYNA expose more of the matte fabric properties to the user, but we still see problems with things like bending stiffness and the behavior inside pretensioners and retractors. The advanced belt fitting mode in Primer lets us use fabric shells over most of the seatbelt route, including through both of the slip rings. Matte fabric is very robust, accurate and stable when unloading. It has the benefits of bending stiffness, and we can use airbag reference geometry to remove any initially stretched or distorted elements. We'll take a look at those in more depth later. The friction at the slip rings and the pressure distribution onto the occupant can now be realistically simulated. With the recent additions of orthotropic friction in LS-DYNA, we're one step closer to fully virtual occupant analysis. The process to fit a seatbelt in Primer hasn't changed. First, we select the parts in the model that the seatbelt will touch during the fitting process. Now though, we can include finely meshed models of the slip rings as the belt will pass through these slots. I find the quickest way to model these is to mesh just the outer CAD surfaces with 1mm shells, extrude them 1mm inboard to make a hollow but solid part, then delete the shells. DYNA will use the outer face of the solids as the contact surface, meaning the slot will be exactly the right width. Keeping a line of symmetry helps when orienting these parts into position. The next step is to pick the points that make up the seatbelt path. To save time, I'll read the path points from a CSV file. This function was added in version 17. I've chosen typical points on the structure, but you'll see 2 points at each slip ring. Making a point either side like this helps us steer the belt through each slot. In both cases, I've chosen a point roughly central to the slot. You can pick nodes on the surface and drag them away using the mouse. The lap buckle points are pretty much aligned with the slot. For the shoulder buckle, it sometimes helps to make the points a bit lower down, as you can see. This is what works for me, but by all means try other methods. If you can get it working with just one point, you'll save a lot of time. On the fitting options panel, you'll see a seatbelt mesh density drop-down from which we can select different preset mesh sizes. Element length and number of rows are still fully customizable on the panel below. The very fine setting gives a 3mm mesh length, and that works well for detailed applications. One tip: if you find the fitting process takes a long time, change the density to fine or medium while doing the test fits, then set it to a very fine for the final run. The Define Path menu hasn't changed, with options to control projection, twist and coordinates at each point. From version 18, the Advanced checkbox activates the new editor, giving us a triad of drag handles at each point and many other controls. The Fitting Options panel now has a new Path Visualization tab, where we can control visibility of the new intermediate points and the handles. Here you'll also find options to show the belt and surrounding shell parts with their true thickness in 3D. Let's take a closer look at one point on the belt path. First, the point itself can be dragged in any direction in the screen plane. Dragging the arrow handles will pull the point in that local direction. Dragging the cube handles will twist the belt. Blue and green twist the plane of the belt at that point. Red cubes break the spline and can give us a sharp change in direction independent of the other side. Right-clicking on these cube handles skews the belt in each local direction. The center of rotation is the original path point, so I recommend using zero projection when setting up the belt path. Let's tackle the shoulder slip ring. I'll activate advanced mode and let's turn off the intermediate points to make things clearer. So with advanced mode, we've now got the drag handles to rotate these points, and I tend to start with the blue handles and make sure they're pointing kind of away from the structure. Then I'm going to left click on the green to align the belt plane with the slot. Now right clicking on the green. And the idea is that we manipulate these until the belt is visibly not penetrating the slip ring slot. So here I'm left and right clicking the red cubes, and I think we're nearly there. I can see a bit of penetration on the side, so that's looking pretty good. Now the green lines are a direct line between each point, and the black is of course the seat belt path. So I'm left clicking and right clicking on the red cubes to align the belt to the green line. A final right click on there. That looks pretty good. I think we're done here. I go into thick shaded, save and do a test fit. We can see the belt is pulled tightly through the slot and there's no contact penetrations or problems there. I think that's good enough for now. We can come back to it later if we need to, but let's move on. So next, let's move down to this point over the abdomen and focus more on the buckle straight away. If I only show the buckle, it's going to make things clearer, and use skeleton image for the belt path. So again, I'm going to rotate the blue twist handles so they roughly point away from the structure, and then left click on these green handles to align the belt plane with the slot. Already that's looking pretty good. Now I can move the red handles to try to fine-tune the belt path either side. Let's lift that up, and I'm going to right click on that red part, and you can see how it deforms the belt angle at that point. Very easy and intuitive after a bit of practice, and that looks like we're nearly done. Let's save and do a test fit. That looks fine. Ignore that kink above that, we'll sort that out later. And let's go and change the local element length from 3mm to 1.5. This works pretty well in LS-DYNA and tends to match the contour of the slip ring better than the 3mm default. When fitting these, if you find that the belt slides along the slot and eventually hits the edge of the slot and then the contact starts to go bad, there is a way around this. What you can do is you can right click, go back into define path and right click on point 8 there and set the local friction to 1.0. This has a special meaning, which is no sliding at all, only getting the shell belt can get closer to the surface but it can't slide. And you can see that solved the problem. I will mention though, if you get a lot of sliding like this, it's possible that your slip ring is at the wrong angle to the belt coming in on both sides, so you might find that rotating the buckle to a more natural angle will solve this without needing friction. To help the belt fit over the lap, we can tweak the points and set curl angle. If I right click on point 9 here, set tweak path curl angle to 30 degrees, you can see the belt is given a 30-degree curvature. That naturally helps it get closer to the dummy surface without penetrating either side. Again, on this point, 30 degrees gets it closer to the final required shape. Tiny adjustment on the center there, and we've solved the lap section. Let's save the belt and do a test fit. And the lap is looking pretty good, but I can see a single point just near the buckle where the belt is penetrating the upper leg of the pelvis there. So a quick rotation of the green and the red and another test fit, and you can see that solved that issue. So we can accept that path and move on to the seatbelt meshing panel, and you can see we've selected the create reference geometry option and just clicking through the mesh steps, and that's given us a very nice shell belt, 3mm length on average, a little bit of stretch just above the pelvis slip ring there, but don't worry about that. Here I'm swapping the nodal coordinates to look at the airbag reference geometry, and it's not very clear, but you can see the rectilinear shape of the reference geometry with a finer mesh where the belts pass through the slip ring. The benefit of reference geometry can be seen in this LS-DYNA analysis. A few elements of yellow and red were stretched by the belt fitter. We can set a load curve in matte fabric to remove the stretch in the first 5 milliseconds. I'll talk a bit more about these settings later. In the analysis, the belt passes smoothly through both slip rings using just regular contact settings: opt equals 2, SP opt equals 3, depth equals 5. In this model I've used quite a stiff coating property for the fabric, but that gives pretty realistic deformation. We'll talk a bit more about the fabric properties later. The mechanism for contact friction between the belt, buckle and pelvis is pretty realistically simulated. Next, let's take a look at fitting a belt over a child seat. In the next demonstration, we're going to fit a belt over a simple version of the Q10 dummy sitting on a typical booster seat at the back of the vehicle. We're going to use a simple model of just the minimum components meshed in the correct location. The best way to get the correct location is to scan the parts in the real vehicle using a scanner attachment on a 3D measuring arm. If you don't have one of those, you could get good photos from all angles and use Primer's background image align tool to line them up and orient the parts into position. If you find the belt doesn't fit through the slots very well, it's likely you've got an unnatural angle with the slip ring, and try rotating them a little bit to make them more natural. Let's start then. If you had include files, now would be the time to set the current layer. Otherwise we do safety, seatbelts and define, create, and we're going to use that title. We select the parts that the seatbelt is going to touch, that is this belt guide, the upper slip ring, the child seat, the dummy, the pelvis slip ring and the seat cushion. These will be different depending on the model. You can sketch them to check that you've got the correct parts selected. I'm going to minimize the keywords and tools panels so we can see more of the seatbelt panel below. Then talk through some of the fitting options. From the top, point projection none works best for child seats as well as path twist. Keep off the auto depenetrate option, and this time I'm going to use fine to begin with and set it to very fine at the very end. Just change the curve angle to 5, doesn't do much. I do suggest you select the correct belt thickness and width for your vehicle that match your slip rings. Don't try and fit a wide belt through narrow slip rings. Depenetrate belt to belt, keep that on, and true shell thickness values works best. Increasing the tolerance to 1E-4 helps us converge a little bit quicker, and trans friction I changed that to 0.5 in this case. We don't want the belt to slide around a lot during fitting because we're going to put it in the right place to start with. Path visualization, the path order mixed I find works best for child seats. You're welcome to try spline as well. Sometimes spline works good as well. This case mixed. And we'll start with skeleton wire. It's worth changing the acute break angle to 10 degrees. That will stop Primer from changing the belt shape to an acute shape when it goes through a tight bend, because we don't need acute angles with no DYNA slip rings. And then finally we're going to view the structure with thin shells, not with thickness. These options can be saved at the top right hand of the fitting options panel, so you can use exactly the right options to start with in your next model. The next step is to define the path, and I will start by picking points on the retractor. You can start at the anchor point if you prefer, but I'm going to pick a point in the middle of the retractor. Then we go to the outboard side of the shoulder slip ring, and I'm going to choose a point just a little bit lower than the slot on the outer side. And then the inboard side, I'm going to pick a point just again lower than the slot, slightly in front of center. Next we have to pick points over the dummy jacket, and it's best to get a nice straight line across the jacket down to the pelvis slip ring. So I like to visually align the slip rings to pick a straight line to try and get a geodesic line across the jacket. In this example, 2 points seems to be good. Bigger dummies can take more points. Next, I find picking a point on the very tip edge of the child seat belt guide helps guide the belt down into the pelvis slip ring. The next point is on the outboard side of the pelvis slip ring, and then we need to pick inside the pelvis slip ring So I'm going to blank the child seat to be able to pick a point on the inside there. Don't worry about getting these 2 points exactly right. We'll be moving them around later. So just try and get them roughly outboard and inboard about level with the slot. The next point we have to come up the belt guide. So I'm going to pick a point forward and away from the 0.6 above it. So you can see there's quite a distinctive gap between those 2 points. Then we're going to go up over the pelvis, and we usually use 3 points on the pelvis, one on the side, one in the middle, and one on the other side. Then finally we can come down off the belt guide, off the seat cushion to the anchor below. Let's have a quick visual check using the thick shaded option. And don't worry about the twist at the moment. We just need to get the general path points down, and as fewer points as possible, but enough to get the belt over the structure. That's looking good. We're going to save and write the model out with a different file name. So from now on, if we make a mistake, we can come back to this point and carry on. Moving on now from the retractor to the shoulder slip ring. Don't worry about the twist at the retractor straight away. Focus on the slip ring position. First of all, I'm going to drag those light blue points to be roughly where I want them, which is slightly away from the slot, but keeping the belt in a sensible path going through it. Then we set the blue twist handles to point away from the structure, and just modifying the points there. Then the green ones to align the belt plane with the structure as we did before. I'm now right clicking on the green drag handles, nearly finished. We can then the red ones to control the belt angle coming into the slip ring and through the slip ring. Using transparency and looking down the line of the slip ring can help us visualize, get that in the slot. It's not very difficult, trust me, after a bit of practice. That's looking good. We'll just save and do a test fit on that. Yeah, no problem with penetrations there. Now we can go back to the retractor and then just fix that. I'm sorry, we're going to look at the belt, set the belt angle coming in and out of the slip ring first of all, just to make sure the belt aligns with the next 2 points. And now we can look at the twist at the retractor end, right clicking on the red and green so the belt comes out of the retractor reel in a sensible angle. I'm going to end up meshing these as 1D belts here and use a real retractor, an LS-DYNA retractor, but if you want to wrap the belt around the reel of the retractor, you can do that manually using the Primer's airbag fitter, but that's a different webinar. Okay, we have now done the retractor to the shoulder, so we're going to go over to the lap. And it looks okay, but if we set transparency of the jacket, we can see 0 projection. Initial projection means we're right in the middle. Try to stay as close to the surface. Don't drag too far off the dummy surface, otherwise it will take a long time to fit the belt and pull it back. So once you've dragged the blue projection points a little bit away, use the red to remove the final bit of penetration. We won't worry about that up there, we'll come back to that one later. Let's now focus on the lap slip ring and get those points in the correct position first of all. That will help sort out the belt path above and below it. So looks like I'm jumping ahead, but really it's worth getting these angles correct to begin with, and then we'll sort the others out later. Right, so we need blue to point away from the structure, then we use left click and right click on the greens, just align with the slot, I'm looking from the inside again now. Just drag it a bit to align with the slot. That's looking pretty good there. I think that looks done. Now we can gradually tweak these other points. So we've got 0.6 and 0.9 have to fit inside the valley of the belt guide but not penetrate. 0.9 is looking good where it is. We just need to drag and reposition 0.6, and I think it could do with some curl angle, so I'm going to give quite a steep 40-degree curl angle and then try and drag it so it can easily fit into the valley of the belt guide. I know from experience in tests that these belts do fit quite deeply into that valley section. That's all right. I think we can improve it, but at least we've got the basics looking good there. We know we need a finer mesh through the slip ring. Just go and check that. Looks like we can move some points a little bit closer there. Again, setting transparency, looking down the axis of the slip ring. Let's just do a bit of fine tuning. No visual penetration, and a test fit. There is a bit of penetration, but it looks fine. It looks fine to begin with, so we can move on. But there's a little bit of improvement here we need. So I'm going to try and drag it out and see if we can get it to fit deeper down in that belt guide without hitting the end of it there. We might come back to these points, but we're going to move on to do the lap to the anchor section. Either side of the dummy hip we use a curl angle. I find 30 degrees works good for the child seat as well, the child over the, and initially drag these points to align the belt plane with the surface of the dummy. The lap is always a difficult part to do because in test the dummies sometimes wear, the adult dummies wear t-shirts and the child dummies have neoprene jackets. If you're using side impact, of course they have neoprene jackets, and that can be significantly different location to the finite element model, the surface of the finite element model. And you want to try to represent the correct amount of slack in the belt system, and of course the height up the pelvis block is very critical for the correct loading on the pelvis, especially in front impact. We don't want too much slack in this belt system, so that 0.13 there, we don't want it with too much curvature, because that will require a lot of belt fitting iterations, and if we let the belt fitter run for a very long time, it's likely to screw up some other parts like the slip rings. So we're going to try and manually remove slack by making the belt as straight as possible. A little bit of fine tuning here just to remove initial penetrations. It really isn't difficult, you've just got to tweak it a bit, try and get it as close to the surface as possible, but obviously not penetrating, as we can see on the side there. I'm going to drag these little bit of tweaking and tuning, and that looks good for penetrations. We can always come back and reduce the slack curvature later, and that looks good down to the anchor. So we are complete for a basic level fit. Now you could stop there, but I want to show you an example of fine tuning for these seat belts. Let me set the retractor to 0.1 and go ahead and try and get this belt path 0.6 deeper into the valley of the belt guide. So I can just drag the blue arrow handle till it penetrates and then back it off a little bit, save and fit, and that's looking good. No contact penetrations. You can see how it slides up the belt guide. That's because the 0.5 above it, as it tightens, it wants to pull it up in a straight line. So we don't really want to run too many iterations. Now, I've mentioned about the importance of minimizing slack. In this model, we can see there is a large amount of curvature in the pelvis to belt guide stretch, and to remove all of that would require fitting for many iterations, during which time other parts of the belt may slide away from their ideal location. So to try and remove this excess curvature, we've got a number of options. I could have inserted another point using insert at point, but I'm going to try and use the existing point we've got here and just move it around a bit. I'm putting in some curl angle to try and get it closer to the belt guide valley. I just need to rotate it a bit to try and remove those penetrations. That seems to have worked. Let's see, we've still got a bit of curvature there, but I think that will be pulled out in a fairly small number of iterations, which will not have any adverse effect elsewhere in the path. Okay, so we have a very good belt fit after 300 iterations in the very fine mesh density mode. Always a good idea to spend time visually checking the path, looking for fidelity to the real belt position, looking at photos and scan data if you have it, and making sure there is no penetrations and also no excess curvature and no unwanted slack in the system. Okay, so the next step is to move on to the meshing panel. In this example model, I'm going to keep it simple. We've got 1D elements going into the retractor up there. You would need more in real life. And we're going to use shells everywhere else. I'll have 0 shells for the end section, just to keep things simple. Now we need to define some properties. I won't go into the 1D seatbelt property discussion here. I'll just create a simple section and material card for that, so we can mesh it. For the shell properties, I'll explain a bit. We're going to make a fabric part, fabric shells, and section shell card we usually use L-form 9, which is the fully integrated membrane, and we're going to define the beta angles. I'll set 0.8mm thickness for the thickness, and then 0 and 90 degrees for the warp and weft of the fabric. We need mat 34, and I'll just input some real typical values here. Of course, you should be using the accurate data from your seatbelt material tests. This is just typical values though. Let's have a high level of damping. We don't need compressive stress elimination. The TSR FAC curve works well with the airbag reference geometry, and I tend to have a curve that starts 0, 0 and rises up to 1 over a short period of time in the beginning of the analysis. This is just like an airbag deployment. So in this case, for example, over the first 10 milliseconds, let me write that correctly, from 5 to 10 milliseconds it's picking up. Let me show you what that looks like. 0 to 1 over 5 milliseconds. AOPT 0 is fine because primer aligns the shells correctly anyway. The transverse direction is the local A axis or the X direction, and we use -14 for the fabric formulation. For -14 allows us to input bending stiffness properties, E-coat, S-coat and T-coat. I find a value of 100 megapascals for E-coat, that's the Young's modulus, and 0.2 millimeters thickness gives a bending stiffness roughly typical that we see in real belts. Please don't take my word for it, use your own test data. As you should also for LCA, LCB, LCUA and LCUB, which are the stress strain curves in loading and unloading for the fabric material warp and weft directions respectively. In this model, when AOPT equals 0, primer creates the local A direction in the transverse across the width of the belt. So for the longitudinal lengthwise direction, LCB would be the stress strain curve of interest. Let's create that fabric property and update. Press generate to finally create this belt. We're going to use the create reference geometry option, so Primer will create that in the background for us, and we can see a nicely meshed belt. If we use the display options to swap nodal coordinates with the reference geometry so we can see it temporarily, we can check there's a nice rectilinear mesh, including the finer mesh section as it passes through the slip ring. So there we have it, a nicely meshed seatbelt over a child seat. Here are some results of a fully fabric seatbelt using the same material properties, the coating properties as I showed you earlier, and the same mesh density. So as long as the slip rings are naturally correctly positioned, you should see them pass through the slot without any hang-ups or catching, and you should also see fairly reasonable behavior at the buckle slip ring. You can see some buckling on the lap section, and that's fairly realistic, but it does occur more with the finer meshed belt. Now this can be reduced slightly by the coat properties, but not completely, and if you really want to reduce all buckling across the lap, I recommend some additional shell stiffeners using matte elastic, just in a couple of rows to make that stiffer. But just blanking the pelvis here, you can see how the belt correctly applies the load to the pelvis bone, so leading to a more realistic pelvis loading situation. Next, I'd like to show two examples of passengers in the rear seats. Here is an example of a 95th percentile on the right hand side rear seat, and it's an interesting challenge because the dummy is very wide. Let me take you through some of the interesting points in this model. The belt comes straight out of the retractor through a guide and then out of the trim through a slot in the trim, then over a very round large dummy torso, and you can see the belt cuts in very sharply around the torso down to the pelvis buckle, which is quite far down and behind the pelvis there, very tight. So we need extra points to cope with this geometry, and we go up over the lap and down to the anchor as usual. If we look at the meshed belt, you can see I've used a variable mesh size. The main belt is meshed in medium size primer fabric elements, that's a 7mm mesh, but where it gets close to the slip ring we go down to 4 and then 3 and then 1.5 through the slip ring as before. And here you can see the reference geometry with the variable mesh. In this next slide I want to demonstrate some more techniques for visualizing the belt going through the path structure. I've already been using transparency and wireframe mode to change the display of these parts, but we can also use cut sections. So here I'm creating a cut section using 3 nodes. Press Y on the keyboard to turn the overlay on and pick 3 nodes down the center line of the buckle, and that's giving me a nice cut section down the center line. You can see I've got a thick cut of 1mm displayed, which helps show the seat belt in the true thickness mode. And because the cut section is down the center, I can pick the belt path points and the drag handles, and this helps me dial in really close to an accurate path as it goes around this buckle. To be honest, you don't really always need this level of fitting, but it can certainly help you learn about the structure. While you're practicing, it can be a very useful technique. One of the right-click options on a path point is View on Point, Center on Point. This will temporarily put the point in the center of the screen and then cause it to be the center of rotation. We can also change the preset views, especially side, front and rear view. That will look down the green axis of that path point. That can be really helpful in aligning the slot and the path point visually. Another right-click option is Reset. Here we can reset any of the attributes that have been set in this current seatbelt session. We can also unset many attributes. Unset will revert the point to the very initial raw condition as if you've just selected the path point. In the tweak path, we can reverse the radial direction, where if you have a curl set up, you can reverse it. And don't forget that middle mouse button will undo any instant change that's just been done. And then tweak path also has a reverse in plane option, which will change the twist like that. We can also set the properties, which can be defined on the right hand seatbelt menu as well. Here we can change a point to be fixed or known, which will mean that it will not move when you apply the belt fitter. That can be useful. And in this example, I'm going to choose the cross section option. So Primer will create a database cross section at that point during the meshing process. As you've seen before, we can change the element length from this point to the next point, and the local friction from this point to the next point during the fitting process. This is an example of a 95th percentile passenger in the mid or rear seat, and this is slightly different in that the retractor is mounted up on the ceiling and there is a belt loop at the back of the seat. Let's go through from the top. The belt comes directly out of the retractor through a belt guide and then through this solid steel loop before passing over the chest and then round to the pelvis slip ring, which is again very far back behind the pelvis, so there's a very narrow gap to fit the belt through. To do these rear passengers, we usually use more points on the belt path than for front passengers, and they can be especially helpful when moving the belt apart. In this example up here, I've made a 3mm mesh section, and I did that by making an extra path points by clicking intermediate points like this. That lets you set mesh size, various mesh sizes throughout the length of the belt. Another point to note, it's worth making a point where the shape changes dramatically, and then you can use those red handles to rotate the belt downwards and avoid any slack by too much curvature. Just a final couple of comments about belt path fitting options. Earlier I said 0 point projection was best. Now that does leave the initial position of the belt penetrating the dummy, and if you use a small fixed distance like 5mm, Primer will automatically avoid that. And that works best for places like here over the chest. But when you have the projection set, you'll see that the belt rotates when we drag it with the handle about the original path point, not the current belt center line. It's perhaps clearer to see in skeleton wire mode. So what does that mean? Well, it doesn't mean very much. You can, if you have 0 point projection, of course the belt rotates about the belt center path, and I actually prefer this. I think it gives you more control, especially at the buckle. We'll go and have a look at that in a minute. So yeah, let's go and have a look at the buckle now, and if I zoom in, this is with point projection applied. Of course it applies to the whole of the belt, so that includes these areas here. And again, if you rotate, you are rotating about the path point, which is sitting right next to the buckle. Now you can manually remove the penetration, but then that affects the mesh size and so on. So I prefer 0 or none for point projection, and then just manually removing the penetration over the jacket points, which is very easy to do. Also, it's worth commenting that when you're fitting the belt through the slot in the slip ring, try to always use thick shaded mode, because that will give you a much better idea if anything is penetrating than the thick wire mode. I also said that the acute break angle should be set to a fairly low value, like 10, and that is because we want primer to mesh the belt continuously all the way around the sharp angled corners. If we set it to the default 90, you can see that the primer thinks these will be slip rings, and so you should set that to a lower value than what you see in the path, so primer will not break the mesh and form a continuous loop of shells. That concludes the live demonstration. Just a final comment about where to find more resources to learn about seatbelt fitting in primer. If you can access YouTube, please check out our Oasys LS-DYNA channel, and in the search bar on the right, if you put in seatbelts, you'll see the short 8-minute overview, and then part 1 and part 2 of the very good seatbelt fitting webinars that were made a couple of years ago. We also host all past webinars on our oasyssoftware.com website. If you go into the past webinars button and then search in there for seatbelts, you should see the same videos that are available on our YouTube channel. Finally, don't forget, from any menu panel in Primer where you see a question mark button, you can access the manual. In this case, the seatbelt manual is very, very extensive. It covers everything you need to know about defining a path, all the different fitting options available, tips and techniques of how to fit successfully around different types of occupants and child seats. And it goes into detail, lots of detail about all aspects of seatbelt fitting. This is a very comprehensive manual. It contains much more information than we can ever give in webinars. So please do check this out if you have time. That brings me to the end of the webinar. Thank you very much for your attention, and I hope that we're able to answer any of your questions and that you give Primer seatbelt fitting a try. Thanks very much again.